So due to some unfortunate incident, we couldn't complete this session earlier, that is yesterday. So that's why the class which had to be uh, basically held yesterday, that has been rescheduled today. So in the previous session, we basically started our discussion with this problem, that is the determination of gross shape load. Column can carry safely at a factor of safety of 2.5 against inertial period, and we have to use the IS code recommendation to determine this load. So for that, all the essential input parameters are given to you, like the shear strength properties of the soil mass are given as 9 kPa, that is cohesion, and the angle of internal friction as 30 degree. Then the saturated unit weight and the bulk unit weight both are given to you, because there is a water table, groundwater table basically is encountered at the foundation level. Therefore, the soil which is above the groundwater table, so bulk unit weight will be basically applicable for that part of soil, and the water table and the soil mass which is below the water table. So for that, you have to use the saturated unit weight. So that's why two types of unit weight, namely saturated and bulk unit weight, are given in this problem. So apart from that, the different safe factors, since the footing which is basically carrying the column load, it's not a straight footing, so it's basically having a shape of rectangular. So that's why you have to also utilize or implement the corrections according to safe factors. So the safe factors, depth factors, bearing capacity factors are also given to this problem. Now to determine the inclination factors, it is mentioned that the load is vertical and acts at the center of the footing. So therefore, inclination factors you can assume as unity for all the components like cohesion, surcharge, and the unit weight. Okay, so we just started with this information that to calculate the gross shape load, first you have to compute the gross shape bearing capacity, then you have to multiply this shape bearing capacity with the area of the footing. So where area would be width times length, since width and length both are given, so it's a rectangular footing of size 2 meter by 3.5 meters. So the cross sectional area would be 7 meters square, 2 times 3.5. So if you multiply this area with the gross shape bearing capacity, then you can easily determine the load which can be transmitted to this column. Okay, so this is the pictorial representation of the given problem. Now, how we can determine this shape bearing capacity? So to determine the shape bearing capacity, first we have to determine the net shape bearing capacity, and we have to add the effective overburden, which is basically existing at the foundation level. That component we have to add with the net shape bearing capacity, then only we can get the shape bearing capacity. Now to determine the net shape bearing capacity, first we have to calculate the net ultimate bearing capacity, and we have to divide it by the recommended factor of safety. Here it's 2.5. Okay, and to calculate net ultimate bearing capacity, you have to calculate the ultimate bearing capacity first, and you have to deduct the net effective overburden which is existing at the foundation level from the ultimate bearing capacity. But as I mentioned earlier, that this IS code recommended the net ultimate bearing capacity directly. Okay, so instead of ultimate bearing capacity, it directly gives the net ultimate bearing capacity, and this is the expression for the bearing capacity, net ultimate bearing capacity. Here, as you can see, so this is the first component, CNC, SC, DC, IC. This is the second component, Q times NQ minus 1, SQ, DQ, IQ. And this is the third component, 0.5 times gamma B, N gamma, S gamma, D gamma, W prime. So this W prime, this is the water table correction factor. So as you know that when there is a water table in the influence zone of the footing, so you have to accordingly basically correct the bearing capacity by different recommendations which are available in the literature. So here this recommendation factor or this correction factor will use in correspondence with the IS code recommendation. Okay, that we will see. Okay, now apart from this W prime, I hope all the entities which are involved in this equation are directly given to you. Like cohesion, this NC, NQ, N gamma are the bearing capacity factors, then SU, SQ, S gamma are the shape factors, DC, DQ, D gamma are the depth factors, and IC, IQ, I gamma are the inclination factors, where B is the width of the footing and gamma is the unit weight of the soil. So the question is, so now for this problem it's a very straightforward problem, since all the data which are required to solve this problem are directly known to you. However, in many cases this should not be the scenario. So in that case, you have to first calculate the shape factors, depth factors, and inclination factors from the given conditions. Okay, so like this soil is basically the footing is basically having a shape of rectangular. So that means the shape factors you can easily calculate utilizing this table. So this table is basically taken from this IS code. So where SC, SQ, S gamma are given for different shapes of footings like rectangular, square, or circular. And to calculate this SC, SQ, S gamma, you only need to know the width and length of the footing. And this is known to you, since width is 2 meter and the length is 3.5 meter for the given rectangular footing. So therefore, you can easily determine the SC, SQ, S gamma, even though these factors are not directly given to you. Okay. So likewise, you can determine the depth factors if you know the depth of the foundation, width of the foundation, and the angle of internal friction of the underlying soil mass. So in this case, the depth of the foundation is 1.5 meter and width of the footing is 2 meter, and the angle of internal friction of the underlying soil mass or given soil is 30 degree. So utilizing this information of depth of the foundation, width of the foundation, and angle of internal friction of the soil, you can also determine the DC, DQ, and D gamma value. Now coming to the inclination factors. So to calculate the inclination factors, you only need to know the angle of internal friction and the inclination of the load from the vertical. So here it's mentioned that the load is vertical and acts at the center of the footing. So therefore there is no need to consider this alpha value will be basically 0. So therefore again IC, IQ, I gamma will be 1. Okay. So in that way you can also calculate the factors even if these factors are not directly mentioned in the problem. Okay. Now one more thing that you should note, that in this problem the type of or the mode of shear failure is also mentioned, like general shear failure. Okay. So as you know, there are two more types of failure which is possible in the field, like local or punching shear. So if this type of information is not given, then first you have to judge by which mode the footing or the soil underlying soil mass can fail upon subjected to some load. So how we can basically justify the mode of failure? So we can basically draw a conclusion regarding the mode of failure depending on the degree of denseness or the angle of internal friction value for purely cohesionless soil, and considering or depending on the stress strain characteristics of the soil mass for cohesive frictional soil. So as we discussed earlier. Okay. So in this case, since this soil mass is basically cohesive frictional because it's having both the components non-zero, 9 and 30 degree. So therefore we can only draw the conclusion that what kind of shear failure or mode of shear failure will be prevailing for this condition, that will depend on the stress strain characteristics of the soil mass. Now this type of data or this type of information is not available with us. So therefore it's explicitly mentioned in the problem that you have to calculate the gross shape load the footing can carry at a factor of safety of 2.5 against inertial failure. Okay, so it's very clear cut that you have to only consider the mode of failure as the general shear. Okay, not punching or local. Okay, so now the remaining task is basically you have to substitute these values appropriately. Okay, so in the appropriate location you have to just substitute the values. Okay, now before going into that part, first we will calculate this water table correction factor. Okay, since this term or this information is not directly given to this problem, rather the water table rotation is basically indicated in this problem. So as per IS code recommendation, okay, so okay, so let me put this information in this slide. So as per IS code recommendation, this W prime, this is basically 0.5 when this dW is less than or equals to dA. Okay, so what is dW? So dW is basically the water table location measured from the ground surface. So this is the dW. Okay, so here dW, as you can see, the dW is nothing but depth of the foundation only. That means 1.5 meter. Okay, so please keep in mind the reference against which we are measuring the depth of water table. So here it is the ground surface. The datum is ground surface. Okay. Now this water table correction factor again would be 1 when this dW is basically greater than or equals to dA plus d. Okay. So that means if we basically draw a line here, though this diagram is not in scale, suppose this distance is b or this depth is b and this is dA, so this is dA and this is b, so total dA plus b. So if the water table is basically lies at a depth greater than dA plus b, then you need not to consider any water table effect on the bearing capacity. Okay, that means the water table basically lies beyond the influence zone. Okay, suppose this is the influence zone, so it lies beyond the influence zone, so that's why you need not to consider the water table effect on the bearing capacity calculation. And when the W prime is basically less than equals to dF, then you have to calculate this water table correction factor you have to consider as 0.5. Now if the case is in between these two, that means dF to d. Okay, so here I am writing, so if this dW is in between dF and dA plus b, so the scenario is like that somewhere where, okay, somewhere here. So the first case, so suppose it's basically in this location or within this location. The next scenario, that is scenario 2, so in this range. Okay, so the arrow indicates the range of what the possible location of the water table. Okay, and this is the scenario 3. This is the scenario 3 that is in between 1 and 2. Okay, so in this way the water table you can encounter inside the soil mass. Now when it is basically above the foundation level or at the foundation level, just at the foundation level, the water table correction factor in the third term would be 0.5, simply 0.5. And when this water table lies basically beyond a depth of dw dA plus b from the ground surface, then it would be 1. That means there is no such water table correction. However, if the water table lies in this zone, this B zone, means the thickness which is basically denoted by B, means from the base of the foundation and means in between the base of the foundation level and the influence zone, so then you have to linearly interpolate this value 0.5 to 1. Okay. Now in this problem it's very straightforward that this water table is basically lying exactly at the foundation level. That means the water table correction factor, so here I am writing, since the water table is located at the foundation level, so which indicates that the W prime value would be 0.5, and this comes from this IS code recommendation. Okay. Okay. Now what about the Q component in the second term? So Q component is nothing but, so this Q, this is nothing but the effective overburden. Now what is effective overburden? So effective overburden in the sense you need not to consider the pressure which is exerted by the pore water. Okay, so since in this case the water table lies exactly at the foundation level, so the stress which is basically imparting by the means the soil mass which is basically which lies above this level, that will be simply the depth of the foundation 1.5 multiplied by the bulk unit weight of the soil mass. Now suppose so this is at the foundation level. Okay, now suppose the water table, if the water table lies beyond the depth of foundation level, there is no question. Okay, so this is dF. Now this water table, if it lies beyond the depth of foundation, there is no question, it will be always the bulk unit weight multiplied by the depth of the foundation. Now yes, I'll start that part, just solving a few problems which we couldn't solve in the previous session. Okay, so immediately after solving this problem, and there is another one problem, so which we basically took as homework problem in session 3. So after solving these two problems, we'll start the supplement part. Okay. Okay. Now the problem is when this water table is basically located in between this depth of foundation. So suppose there, so that means this is dW and this distance is A. Now for the calculation of effective overburden, you have to consider bulk unit weight and the submerged unit weight both. So that means this Q would be gamma bulk multiplied by dW plus gamma submerged multiplied by the remaining portion. This part is basically under submerged condition. Okay, so since there is no such problem arised in this case, so therefore this Q would be simply gamma bulk times dA. So that means 18 multiplied by 1.5, that means 24, 27. Okay, now just we have to substitute this values in this equation. So QNU, it would be 9 kPa, then the NC value is 30.14, SC value is 1.114, DC value is 1.26, and IC value is 1. Then this Q, we have calculated it as 27, NQ minus 1, so NQ value is 18.4 minus 1 multiplied by the SQ, again 1.114, then DQ is 1.131, and finally 0.5 times. Okay, so for gamma component, that is basically for this soil mass beneath the foundation level. Okay, so it will be the saturated unit weight, so it will be 19, then the B value, this is 2, and the N gamma value, that is 22.4, then the S gamma value 0.77, and D gamma, it's 1.13, I gamma 1, and the water table correction factor 0.5. So if you calculate, then this value I think would be 1157.3. Okay, again here I am writing this the significance of this statement, that IC, IQ, I gamma is all at 1. Okay, now after calculating QNU, you can calculate QS. So QNU divided by factor of safety plus gamma times TL. So 1157.3 divided by 2.5 plus 27. So this value would be, I hope, 489.92. So this is the safe bearing capacity. So therefore the gross safe load, it should be multiplied by the area, that means B times L. So 489.92 divided by 2 times 3.5. So finally the value would be 3429.4. Okay, this is the answer. Okay, so now coming to our second problem, a square footing of 4 meter side is placed at 1 meter depth in a sand deposit. The dry unit weight of sand is 15 kilonewton per meter cube. The footing has an ultimate bearing capacity of 600 kPa. Consider the depth factors dq d gamma 1 and the bearing capacity factor n gamma equals to 18.75. This footing is placed at a depth of 2 meter in the same soil deposit. Now for a factor of safety of 3, as per Terjagi's theory, the safe bearing capacity of this footing would be. Now, as we can understand from this problem statement, so two scenarios are talked about. So first, scenario 1. So in scenario 1, so this is a square footing of size 4 meter. Now this is placed in a sand deposit at a depth of 1 meter. So this is df equals to 1 meter, and as per Terjagi's theory, the ultimate bearing capacity is calculated as 600. Okay, now coming to scenario 2, now the same footing of size 4 meter, square footing obviously. Now the depth of foundation is basically increased twice. Okay, so first it was 1 meter, now it's increased to 2 meter. So you have to now calculate the safe bearing capacity as per Tirjaghi's theory. Now please check that as per Tirjaghi's theory, this Q ultimate, because to determine the Q safe, first we have to calculate, or we have to start from Q ultimate. So Q ultimate, it would be 1.3 times CNC plus gamma df NQ plus 0.4 gamma dn gamma, and this is obviously for a square footing, incorporating the or considering the safe correction, safe factors. So this 1.3 and this 0.4, this is considering the safe factors. Okay. Now, since the soil is basically purely cohesionless, this is sand. So the footing is basically placed on a sand deposit. So this component, this term will be 0. So cohesion will be 0. So only two terms will be remaining there. So gamma df NQ plus 0.4 gamma b n gamma. Now please observe that for the given soil, nowhere in the problem statement the angle of internal friction value is mentioned. Rather, the corresponding bearing capacity factor contributed by the unit weight of the soil mass is given, that is 18.75. So this term is given. This term is given n gamma. Now to calculate the QU, you need to know NQ as well. So this is not given. So this is only given. So gamma you know, df for both the scenarios you know, again gamma you know, and the width of the footing you know, because the soil mass is basically in both the scenarios the soil mass is not changing, it remains constant. You are dealing with the same sand deposit and you are dealing with the same size of the footing, that means a square footing of 4 meter side. Only the depth of the footing is basically changing. So obviously if you utilize the ultimate bearing capacity value for corresponding to scenario 1, you can easily determine the NQ value. How? Because QU equals to 600 kPa. This is for scenario 1. Now if you substitute the values, that means gamma value is given as how much? So the gamma value is given as 15 kilonewton per meter cube. Now if you substitute these values, 15 multiplied by df, df is 1 for scenario 1, then NQ plus 0.4 times 15 times 4 times the n gamma value is given as 18.75. So 18.75 equals to 600. So if you solve this equation, you will end up with the value for NQ as 10. Okay. Now if you know the NQ and n gamma both, and the soil mass is not changing, you are dealing with the same sand deposit, so therefore you can obviously calculate the ultimate bearing capacity corresponding to scenario 2, that is the same footing but with a depth of foundation as 2 meter. Therefore this would be 15 times 2 times 10 plus 0.4 times gamma is 15 multiplied by 4 multiplied by 18.25. Oh, sorry, 18.75. Okay, so this is 18.75. So if you calculate, then this value, I hope it would be 750 kPa. 750 kPa. But you have to report the safe bearing capacity with a factor of safety of 3. Therefore, Q safe, it will be simply QU minus gamma df divided by factor of safety plus gamma df. So that means 750 minus 15 multiplied by 2 divided by 3 plus 15 multiplied by 2. So this is 720 divided by 3, that means 240 plus 30. So okay, so this would be the answer for the given problem. So when the depth of footing or the footing is placed at a greater depth of 2 meter in the same soil deposit, so with a factor of safety of 3 as per Tejaghi's theory, the said bearing capacity of the footing will be 270 kPa. Okay, so with this problem, we basically come to an end for the bearing capacity discussion. Now we'll start discussing about the about a new topic that we have learned from week 4, that is the calculation of settlement for shallow foundation. Now this settlement of shallow foundation can be of 3 types. So immediate settlement, primary settlement, secondary settlement. So rather saying it's of 3 types, it will be better that the settlement is basically consisting of 3 components. So first of all, immediate settlement or elastic settlement, then the second component is primary settlement, and the third component is secondary settlement. Now from the very basic fundamentals that you know, that immediate settlement, it is basically the component which is occurring during the application of the load. So it's basically occurring immediately after application of the load or during application of the load, and mostly or mainly less than 7 days. Okay, now this primary settlement, it comes from basically due to the consolidation part, and the secondary settlement is contributed by the rearrangement of the soil particles but at a constant effective stress. Okay, so when there is no change of the loading, so only the particles are basically rearranged inside the soil matrix, so you will be basically expecting some kind of settlement, and that settlement will be secondary settlement. So these are the 3 components which will constitute the settlement of a shallow foundation when it is subjected to some external loading. Okay, now for different type of soils, or depending on the nature of soil, you may expect that for some soil only the immediate settlement will constitute the whole part or will contribute to the whole part. In many cases, primary settlement will constitute or contribute to the whole settlement. Similarly, for some soil, secondary settlement will be only applicable entity. Okay, so please basically go through that details. So where this immediate settlement will be valid, where primary will be valid, where secondary, and where all of these 3 will be valid, or a combination of immediate primary will be valid, or primary secondary will be valid. So in this way. Okay, now how we can calculate the settlement? Now this settlement calculation, consolidation, so we can easily, so okay, one more thing that we should keep in mind, that as per the scope of this course is concerned, so we will be only dealing with these 2 parts. Okay, so the first 2 components will be only dealing with, so this part and this part, so immediate settlement and the primary settlement. Okay, now for calculating the primary settlement, we can go for this Tejaghi's 1D consolidation theory, and we can easily determine the primary settlement. So, and as you know that for a purely cohesionless deposit, this immediate settlement will cover or will constitute the whole settlement, and for purely cohesive soil, this primary settlement will be mainly valid. However, for cohesive soil, there will be some immediate settlement component as well. Now for cohesive soil, you can use the elasticity theory to calculate the immediate settlement, that we will know in the subsequent discussion, and Tejaghi's 1D consolidation theory to calculate the primary settlement. However, for cohesionless soil, it's very difficult, and we have discussed about this in the earlier sessions as well, that to extract some soil sample, undisturbed soil sample, for determining the settlement in the laboratory or through laboratory investigation, it becomes very difficult, because the structure of the soil mass, it got very disturbed during the sampling procedure. So therefore, to determine the immediate settlement for purely cohesionless soil or cohesionless soil, several in situ methods are basically available in the literature, like plate load test, method based on SPT, method based on SCPT, or different semi-empirical method as suggested by Buisman 1914. So one reference is basically given here. So please keep in mind that all these methods are for determining the immediate settlement or the settlement of cohesionless soil, because for cohesionless soil, immediate settlement is the total settlement. Okay, now apart from these two topics, that is the different types of settlement for shallow foundation and the calculation procedure for settlement of shallow foundation, we have also learned how to calculate the ultimate bearing capacity and the safe bearing capacity from the data of plate load test. Okay, and one problem is basically solved in details by utilizing the data of plate load test by our professor. So those who are still pending to go through that part, so I'll request all of you, please go through that part very quickly. Okay, so you can easily understand if you basically go through that part or solve the problem by your own. So in this problem, in this session, we'll basically take up very few selective problems, and we'll basically try to understand how the settlement components are calculated and on what basis, means by what procedure. Okay, so if it is primary, then we can easily go for this Terzaghi's one-day consolidation theory, and it's immediate, we can basically go for any of these methods, method based on plate load test, method based on SCPT, method based on SPT, or some semi-empirical method. Okay, now one slide, this is also basically taken from this with lecture content. So this slide nicely summarizes all the methods which are basically required to calculate the settlement components, immediate and primary. So first of all, immediate settlement, this is for clay. So this expression is basically derived utilizing the elasticity theory, and this is for the consolidation settlement for clay. As I discussed, that this is basically considering the Terzaghi's one-day consolidation theory. Now coming from settlement of cohesionless soil, that is immediate settlement, you can go for any of these methods as I listed here, and these are some expression concerning this method based on SCPT. Okay, so we'll see how to utilize this method to calculate the immediate settlement for granular soil or sand. And one more thing that you should also learn, or we have learned from this week, that is regarding different types of corrections which are basically we have to incorporate at the end. So these are like depth correction, rigidity correction, and the pore water pressure correction. And we'll also keep in mind that, or we should keep in mind that under which circumstance we have to implement this type of correction. The depth correction, it's basically valid for all this type of settlements, that is immediate and primary settlement, because this settlement expression is basically derived based on this assumption that the footing is basically resting on the surface of the soil. That means as if this is a surface foundation. So no embedment for the foundation is considered during the derivation of the settlement. Okay. However, in the actual scenario, there is some embedment, because rarely it's seen that the footing is basically placed on the surface of the soil mass, because it is the more vulnerable condition. Now to get better benefit, this foundation is basically always preferred to have a foundation, depth of foundation 1 meter, 1.5 meter, 2 meter, as we have seen in the previous problems. So therefore, this depth correction factor you have to incorporate for both these settlements, immediate and primary. Now coming to rigidity correction, so as it is mentioned in bracket that this is for wrap foundation. Now rigidity means if the footing is flexible, means again this calculation is basically valid for a flexible footing. So therefore whenever you will encounter some rigid foundation, you have to accordingly incorporate the rigidity correction, because rigidity will try to reduce the settlement which you expect. Okay, so the settlement which you calculated on the basis of flexibility, so that will not be the exact scenario. So due to rigidity it will try to reduce, so therefore you have to accordingly incorporate the rigidity correction. Now coming to pore water pressure correction, and again this part is valid only for consolidation settlement. So this consolidation settlement expression, this is derived on the basis of 1D consolidation theory. Now if you go through the consolidometer test, so if this is the consolidometer, so this radial direction is basically confined, so no movement along the radial direction is basically allowed. So only the movement or settlement is allowed in the vertical direction. So that means you are considering only 1D consideration, or you are not means considering 1D consideration. It's basically the one of the assumption of the Terzaghi's 1D consideration theory. But in real life this phenomena is not valid, because in real life this radial confinement, to some extent this radial restraining condition, this is not valid. So you have to consider for 3D consolidation, and that's why this pore water correction factor comes into picture. Okay, so this is all about the types of corrections and its validity depending on the circumstances. Now we'll take one sample problem for calculating the consolidation settlement through this problem 3. So where a footing 2 meters square rests on a soft clay soil with its base at a depth of 1.5 meter from the ground surface. The clay stratum is 3.5 meter thick and it's underlain by a firm sand stratum. The clay soil has liquid limit 30%, the specific gravity of soil solids 2.7, water content at saturation 40%, and the undrained cohesion as 50 kilonewton per meter square. It's known that the clay soil is normally consolidated. So very important stuff. Compute the consolidation settlement that would result if the load intensity equal to safe bearing capacity of the soil were allowed to act on the footing. Natural water table is quite close to the ground surface, and take factor of safety as 3. Assume load spread of 2 vertical is to 1 horizontal, and use Terzaghi's analysis to calculate the safe bearing capacity, and it's explicitly mentioned that do not apply any corrections. Okay, so if we try to visualize the problem looks like this. So where this is the square footing of size 2 meter. So this is the square footing of size 2 meter. Now this footing is placed at a depth of 1.5 meter from the ground surface, and it's placed in a clay stratum which is having a total thickness of 3.5 meter, and this clay is underlain by a firm sand stratum. Okay, so that means if we place this footing at a depth of 1.5 meter of a total thickness of this clay stratum 3 meter, so therefore the remaining depth or remaining thickness of the clay below the foundation level would be 2 meter, and after that it's encountered the soil mass is firm sand stratum is encountered. Okay, now what we have to calculate? We have to calculate the consolidation settlement that would result if the load intensity equal to safe bearing capacity of the soil were allowed to act on the footing. That means the load, the intensity of loading is not directly given to you. First you have to calculate the safe bearing capacity of the footing or of the soil mass, and then you have to apply that at the load intensity at the foundation level, and due to the application of this load you have to calculate the consolidation settlement. Now a few things that we should keep in mind. First of all, this clay stratum is basically supported by a firm sand stratum, so therefore there is no question of calculating the consolidation supplement of firm sand stratum. So whatever supplement it will experience, so it will be simply this, what we can say, elastic or immediate. Okay, and again this is a firm sand bed, so you can basically visualize some rigidity condition or fixity condition means below this clay stratum. So my concern only is about to calculate the consolidation supplement of this clay layer of thickness 2 meter. Though the total thickness of the clay stratum is 3.5 meter, but since the foundation is basically placed at a depth of 1.5 meter from the ground surface, so only this part will be impacted, because the foundation load is basically starts spreading from the foundation level. Okay, and the dispersion angle is also given. So this is 2 vertical is to 1 horizontal. So with this angle or with this dispersion angle, the load intensity which is basically applied at the foundation level is getting distributed in the underlying soil mass. Okay, and further what you have to consider, this settlement calculation without applying any correction, because since we are calculating consolidation settlement, 2 types of corrections will be valid for this scenario. First of all, depth correction factor, and secondly the pore water correction factor. Okay, but will not apply this correction since it's mentioned that there is no need to apply any corrections. Okay, now we'll start calculating the consolidation supplement for the given square footing of size 2 meter. Now, based on Teljaghi's 1D consolidation theory, if you can remember, this consolidation settlement expression is given as Cc divided by 1 plus E0 times H log of sigma 0 prime plus delta sigma divided by sigma 0 prime. Okay, so please correct me if I am wrong. Now, what is this Cc? So this Cc, sorry, this Cc, it is defined as compression index, and you all know. Okay, I hope you all know about this terminology. So compression index. Now what is this compression index? So compression index basically, now when you basically perform this consolidometer test, so you plot the data of this test in this fashion. So E versus, that is void ratio versus effective stress, and this is a semi-logarithmic plot. Now the behavior after plotting the test data obtained from the consolidometer test, the behavior of this plot would look like something like this. Okay, now the gradient of this lower linear part, almost linear part, will give you the compression index Cc. So that means the Cc is nothing but delta E divided by log of, suppose this part will give you the delta E, and this is the delta sigma. Okay, so this is delta sigma. So delta E divided by log of delta sigma, or rather we can say it would not be delta sigma. So suppose if this is sigma 1 and if this is sigma 2, so sigma 1 divided by sigma, oh sorry, sigma 2 divided by sigma 1. Okay, so this is the negative gradient. So this is decreasing. So with the application of the load or with the rise of the effective vertical stress, the void ratio is getting decreased. Okay, so this is the negative gradient. So anyhow, you have to consider the positive value. So delta E divided by log of sigma 2 by sigma 1. However, if we consider this problem statement, so here this kind of data is not given. So what is the change in void ratio due to means how much change in loading? So this kind of data is not given. Now then, how we can determine this compression index? So we can determine this compression index based on some empirical correlations. Now one correlation is like this, that CC is 0.009 times LL minus 10. Okay, so this is one correlation for calculating the compression index when there is no such data. This void ratio versus effective stress is given to you or is available with you, so you can utilize this correlation. Now for this problem, the liquid limit is 30%. So 0.009 times 30 minus 10, so it will give you the compression index as 0.18. Okay, so 0.18. Okay, this is the first term. Now what's about this E0? So E0, this is the initial void ratio. Okay, this is the initial void ratio. And how you can calculate this value? So you can calculate this value utilizing the three-phase relationship. How? So you know this expression, this relationship, WGS equals to AC. So it's derived on the basis of three-phase relationship. So here W denotes the water content, GS denotes the specific gravity of the soil solids, S denotes the degree of saturation, and E denotes the void ratio. Now what will be the value for E? So E will be simply WGS by S. Now one point to note that for this problem, one statement is given, like it's known that the clay soil is normally considered. Okay, no, this is not the statement. Natural water table is quite close to the ground surface. So the water table is basically located at the ground surface. So therefore, the entire clay stratum is under full saturation. So S value would be simply 1. So therefore, this E0 would be W times GS. That means the water content now is given to this problem 40%, and the GS, this is also given to this problem as 2.7. Okay, so that means 1.08. This is the initial void ratio. So this is also known to us. Now what is H? So H is basically the thickness of the clay stratum, and please keep in mind this thickness doesn't correspond to the whole thickness as far as this problem is concerned. So this thickness only corresponds to the thickness of the clay stratum, which is influenced by the application of the load intensity at the foundation level. So, and you should know that this influence zone is basically extended by a depth of 2 times B from the base of the foundation. Though this depends on the type of footing, means shape of the footing, strip, rectangular, circular, square. So you can basically take the influence zone, depth or thickness of influence zone as 2 times B, where B is the width of the footing. So this is, and how this is basically referred, that you can go for the concept of pressure valve. Okay, so the concept of pressure valve is like that. If you draw the stresses of some fraction of the applied stress, suppose here the applied stress is Q. Okay, we are denoting, okay, or suppose this is Q. Now we are first identifying the points where, means beneath this foundation inside the soil mass, where 0.1 times Q is the vertical stress intensity. Because as you know, this stress will basically getting dispersed or distributed inside the soil mass. So the intensity which was at the foundation level, now that will reduce if you go below inside the soil mass. So in this way, if you connect all the points where the vertical load intensity is 0.1 times Q or any fraction of Q, and if you connect those points by a line, so in that way you will basically be getting some bulb fashion. Okay, so for point load, it will look like this. Okay, so these are called pressure bulb. It looks like something bulb. Okay, so that's why it's called pressure bulb. Now for determining or for deciding the influence zone, many times it's recommended that the depth up to which this load intensity is 0.1 times, means 10% of the applied load, and in that way it's basically fixed 2 times of the weight. Okay, so now if we consider the influence zone as twice of B, now here B is 2 meter, so 2 times 2 multiplied by 2, that means 4 meter. However, we are getting the clay stratum thickness as 2 meter, so that means less than the influence zone, and again the clay stratum is underlain by a firm sand stratum. So therefore there is no need to consider this firm sand stratum into the calculation of conservation supplement. So whatever thickness you are getting within this influence zone, you have to calculate. You have to consider for the calculation of conservation. Okay. Okay. So therefore, this is the thickness, and this is, for this problem, this value is 2 meter. And how we are getting 2 meter? Just now we have explained. Okay. So we know Cc, we know E0, we know H. Now coming to sigma 0 prime. Sigma 0 prime, this is the initial effective overburden pressure. Sigma 0 prime, so this is the initial effective so sigma 0 prime, so this is the initial effective overburden pressure, where at the center line of the influence zone. Okay, so of the influence thickness. So if you encounter in the field scenario that within influence zone there is 2 clay layers, and both the clay layers having different properties, then you have to calculate this sigma 0 prime individually, means for layer 1 at the center line of layer 1, and then at the center line of layer 2. Okay, so for this problem it would be something like here. The center line is basically marked, so it would be 1 meter below the foundation level. Now what will be the effective stress at this level? So it's very simple. It is the multiplication of the unit weight and the corresponding height. Now if we come from this ground surface, so first we have to calculate the total stress, then we have to subtract the pore water pressure at this level from the total stress, then we can easily determine or get the effective stress. Or in other way, we can simply calculate this as gamma submerged multiplied by z. Now what is z? So z is this distance. Okay, so this is z. Now what is the value of z for this problem? So it will be 1.5 plus 1, that means 2.5 meter. And what is the value of submerged unit weight then? So the submerged unit weight, it's mentioned in this problem? No, it's not mentioned in this problem. However, we can calculate the submerged unit weight. So gamma submerged, it's basically gamma sat minus gamma w, and it would be gs minus 1 divided by 1 plus a multiplied by gamma w. Now we know this gs, we know this c, and gamma w we can take it as 10 Newton per meter cube. So gs is 2.7 minus 1 plus 1.08 10. So this gamma submerged would be 8.17 kilonewton per meter cube. So this would be 8.17 multiplied by 2.5, so 20.43. Okay, so we have determined the sigma 0, right? So the only unknown entity is delta sigma. Delta sigma, this is the stress increase. So additional stress increase at the center line of the influence thickness. Again, since this soil mass is basically homogeneous, so therefore we are considering only one layer, as if one layer. However, for encountering cohesive soil with layered configuration, you have to consider this delta sigma in that fashion. Okay, means individually delta sigma at the center line of each layer. Okay, this is the additional stress increase. Now how we can calculate this additional stress increase? So this additional stress increase we can calculate considering this load dispersion as it's given in the problem or mentioned in the problem. So 2 vertical is to 1 horizontal. Now if we consider this load at Q, this load as Q, so it will be Q divided by, suppose this dimension we are taking as Z1, so it will be simply B plus Z1 multiplied by L plus Z1. Okay, so if we draw to vertical line, from two edges, so this value is basically B. Now this distance we have basically covered. Okay, so during the load distribution, so this value would be Z1 by 2, since the distribution is taking place at an angle of 2 vertical is to 1 horizontal. So this distance would be Z1 by 2, and again this one would be Z1 by 2. So a total of B plus Z1 plus 2 plus Z1 plus 2, that means B plus Z1. And similarly, in the length direction, we will be having the distributed length or the dispersed length at a depth of Z1 measured from the foundation level as L plus Z1. Now, since this is a square footing, so in this case, it would be Q divided by B plus Z1 square. Now, what is Q? Now, Q in this problem, this is simply QS, shape bearing capacity, multiplied by the area of the footing. That means B square. Okay. So here we are substituting this Q as QS B square. Now, the major part or the fundamental task remains to calculate this QS, that is the gross shape bearing capacity. So again, we have to go for the calculation of gross shape bearing capacity. So based on Tirjaghi's theorem, this is the calculation of QS. Now, as you know that this is QU minus gamma df divided by factor of safety plus. Now, as per Tirjaghi's theory, what is QU? So QU is 1.3 NC plus gamma df NQ plus 0.4. Okay, so this is only valid for square footing. Okay. Now, since the soil is basically cohesive in nature, so that means phi value is 0. And since this phi value is 0, so the bearing capacity factors would be NC would be 5.7, NQ would be 1, and N gamma would be 0. Okay, so that means this third component will basically vanish. So leaving only the first two components. So 1.3 CNC plus gamma df. Now, if you substitute the values of C, so C is, I hope it's 50 kPa. Okay, the undrained cohesion value is given as 50 kPa. NC value is 5.7. Again, the gamma df. So gamma, you have to take it as 8. Okay, already we have calculated. So it would be basically the submerged value, because here the water table is located at the ground surface itself. So 8.17. So this is gamma sub for the specific problem, multiplied by 1.5. So 1.3 multiplied by 50 multiplied by 5.7 plus 8.17, 1.5. So 382.76 kPa. 382. So QS, it would be 382.76 minus, so for this problem it would be gamma sub, and this is 8.17, 1.5 divided by the factor of safety. Now, what is the factor of safety mentioned in this problem? So this is 3. So the final answer, sorry, not the final answer. So the shape bearing capacity would be 135.76. Okay, so this much intensity a loading intensity is basically applied here. This value is basically 135.76. Now, if this is the intensity of loading at the foundation level, obviously we can calculate the total load which is basically applied. So this is nothing but area multiplied by this intensity of loading. And if we divide this by this dimension b plus z1 square, z1 is basically any depth you can consider beneath the or from the foundation level. So you can basically get the distributed state, means the stress at that level. So therefore now we'll calculate the delta sigma. So delta sigma, it would be qs, so 135.76 multiplied by 2 divided by 2 plus z1. Now what is the value of z1? So it's simply 1 meter. Okay. So it would be 60.34 kPa. So this is the additional stress increase at the center line of this influence thickness. So this is basically 60.34. So now it becomes very easy to calculate the consolidation supplement. So it would be Cc 0.18 divided by 1 plus E0, 1 plus 1.08 H2 log of sigma 0 prime. Sigma 0 prime value, I hope this is 20.43 plus 60.34 divided by. So after calculation, this would be 0.103 meter. 103. So this much settlement we will expect due to the application of this load. Now, a few things we should discuss. That first of all, this clay soil is normally consolidated. So that means this soil never experienced this much load in its past history. So this is the first time it's basically experiencing this much amount of load. So it never experienced load greater than this value. So that's why this is defined as normally consolidated, and you should know. But for over consolidated, the present stress, this is less than the stress which is basically experienced in the past. The present stress which is basically experienced by the soil is lesser than the stress is experienced in its past history. So that is called over consolidated soil. Now, if the soil is defined as over consolidated, the scenario will be changed. So for calculating the consolidation settlement, instead of this one component, so this expression will be modified as Cs 1 plus E0 H log of sigma C divided by sigma 0 plus Cc1 plus E0 log of sigma 0 plus delta sigma by sigma p. It will be better to write it as sigma. Now what is sigma p? This is the pre-consolidation pressure. Pre-consolidation pressure in the sense, this is the past maximum pressure which is experienced by the soil mass. So this information you should know, and this soiling index you should know to calculate the consolidation supplement for an over consolidated clay layer. Okay, because Cc you can easily calculate from this empirical relation, and Cs it's taken as almost 1/5 to 1/10 of 6. And if you calculate, then you will observe that for the same intensity of loading, the consolidation settlement will be much lesser for over consolidated clay as compared to the normally consolidated. Okay. Okay, though this is not the case for this problem. Now, this is for the calculation of consolidation settlement. Now, if we are asked to determine the total settlement of the soil mass, which is basically beneath the foundation, and due to the same intensity of loading, now we have to additionally calculate the elastic settlement part of the clay. Now, how we can calculate this elastic settlement part? So we can calculate this as QNB 1 minus mu square IF divided by. Okay. So this is the net intensity of loading at the foundation level, B width of the footing, Poisson's ratio, influence factor, and E is the elasticity modulus of the clay soil. So this will give you the elastic component of the settlement experienced by the clay layer due to the application of this Qn. Now Qn we know, it's good. B we know. Now these three parameters, that is Poisson's ratio, influence factor, and the elasticity modulus, we don't know. Now for this calculation, if this type of question is basically asked, obviously this type of information will be with you. However, this value we can again calculate, these values we can again calculate from some relationships or what we can say, some tables which are provided in the literature. Like normally consolidated clay, since this clay is mentioned as normally consolidated, so the elasticity modulus would be in between 750 times to 1200 times of ACU. Here ACU is nothing but the undrained cohesion CU, as mentioned in this problem. Then for saturated clay, now for this given problem, the soil mass is clay and again it's saturated. So the Poisson's ratio will be in between 0.4 to 0.5. And you can consider this footing as a flexible foundation, and if you calculate the settlement at the center of the footing, so for a square footing, since this is a square footing, you can take the influence factor as 1.12. Now why I am referring to this tables or to this information? Because in the actual case or in the actual scenario, all this information will not be with you. Means apart from the exam conditions, so it's well and good, all the information will be directly given to you. However, when you will be designing as a geotechnical engineer, or when you will be calculating the settlement, total settlement of a clay layer, so we have to consider both the components, consolidation part as well as the elastic part or the immediate settlement part. Now for calculating that value, you have to gather all this information by your own. So no one basically is to provide you this information. Again, the geotechnical investigation report will be with you. So by going through that geotechnical investigation report, you can get or you can obtain this information. What is the undrained cohesion? What is the Poisson's ratio? Something like that. In some cases, you can also get the elasticity modulus as well. Now you have to decide what kind of foundation is it, where to calculate the settlement, and what should be the corresponding influence factor for calculating the immediate or the any type of settlement. Okay, so this is for the elastic settlement calculation part for a clay layer. Now after calculation, so this is the uncorrected part, though it's not needed to correct these settlements as per the problem statement. However, if it is needed or in the actual scenario, you have to obviously go for this type of corrections. So first, for consolidation settlement, you have to apply two types of corrections, that is this depth, and secondly for pore water pressure. Okay, if the footing is considered to be flexible. So there is no need to incorporate the rigidity correction. So this is for the consolidation component. And for the elastic component, only the depth correction. And this is on assumption the footing is flexible. Now for calculating this depth correction, you have to refer this depth correction for both the elastic as well as consolidation. We have to refer this chart. This is known as Fox chart. Okay, we'll see in details in one of our today's problems in the subsequent discussion, and this is given in the IS code 8009 part 1 1976. And for pore water pressure corrections, either you can go for this chart, that is settlement coefficient versus the pore pressure coefficient. But if you don't know the pore pressure coefficient value A, then you can basically choose the value for this pore pressure correction factor according to the type of clay, whether this is very sensitive or normally consolidated or over consolidated or heavily over consolidated. So for this problem, the soil is normally consolidated, so you can take the value in between this 0.7 okay. So this is for the pore water pressure. Okay, so this is all about problem 3. Now we'll take another problem for calculating the elastic settlement for a sand deposit and utilizing the data of an in situ test. Okay, so we'll see. So figure 1 shows a 2.5 meter square footing resting on a sand deposit. The net pressure at foundation level is 200 kPa. The variation in cone penetration resistance with depth is simplified as shown in figure 1. Determine the settlement of the footing using the Deb and Martens approach. The groundwater table is located at a gutter depth. Assume load spread of 2 vertical is to 1 horizontal. Now, unlike the previous problem, here the groundwater table is located at a gutter depth. So there is no need to consider the groundwater table effect on the settlement calculation. Okay. Now, what is depicted in figure 1? So figure 1, first of all, it basically gives the information about the footing geometry. That means what is the depth of the footing, what is the width of the footing, how much load is acting at the net load is acting at the foundation level. Then it gives a variation of the cone penetration resistance along depth below the foundation level for calculating this settlement, elastic settlement. Though it's not mentioned whether it's elastic or consolidation. However, it's very obvious that for a sand deposit, the total settlement will be solely contributed by the elastic settlement. There is no scope of consolidation settlement. Okay. Okay, now what is the approach recommended by Deb and Martens? So Deb and Martens, they gave the expression of immediate settlement like this: summation of 2.3 H by C log of sigma 0 prime plus delta sigma. Okay. Now, what is H? First of all, you need to justify why this summation sign symbol is basically placed prior to this expression. So, in the previous problem, I mentioned frequently that in the field scenario, you may be having instead of one homogeneous layer, 2 or 3 layers, or in other words, we can say a layered soil mass in the influence zone, the zone which is influenced by the footing. And this is the scenario which I was referring in that problem, that is problem 3. So luckily in problem 3 we have got one layer, one homogeneous layer where all the properties were constant throughout the depth. However, it is more practical to have some layered configuration instead of only one single layer. So that's why whenever you will be encountering this type of problem, so in that case you have to calculate the settlement individually for each layer. So you cannot basically means you cannot perform the settlement calculation as a whole for all these layers. So you have to consider separately all the layers or individually all the layers, and then you have to sum it up the settlement which you have calculated for the individual layer. Now how you can do this layering, or what is the basis of this layering? So either this layering is very straightforward, it's clearly mentioned. Okay, so suppose I am showing in this fashion that this is one layer 1, then this is layer 2, and this is layer 3, and all these layers are within the zone of influence. Zone of influence in the sense 2 times of the B. Okay, here we are taking the zone of influence as 2 times of the B. So this dimension is your Y speed. So within this influence zone, 3 layers are basically coming into picture. So therefore you have to calculate the settlement individually for each of these layers. For layer 1, layer 2, layer 3, and then you have to add, and you will be having the final settlement. Now for this problem, this is not the case, because this layering is not given to you. Rather, you have to go for this layering details based on the SCPT value, that means the cone resistance value. Now here the basis will be the thickness where the cone resistance is more or less uniform. So depending on the cone resistance value, you have to first divide the entire soil mass in the influence zone into small layers. Okay, now as you can see, so the foundation level is taken as the datum, so 0. So now it's basically shown as from 0, 0, 1, 2, 3 marked as the y-axis is marked as 0, 1, 2, 3, 4, 5, 6, like this. Now first we'll determine the zone of influence, the thickness of zone of influence. So where this would be up to a depth of 5 meters. Why? Because the B value is given as 2.5. 2 into 2.5 equals to 5 meters. So this is the zone of influence. Now within this zone of influence, as you can see, the cone penetration resistance first varying from 3 kPa for the first 1 meter thickness, then it's 3 to 4 kPa for the next 2 meter thickness, then 4 to 7 for the next 1 meter, and 7 to 3 for the subsequent or for the remaining part. So therefore we can basically divide this entire influence zone into 4 layers. Okay, so we'll see here. So this entire influence zone we can divide into 4 layers, like layer 1, layer 2, layer 3, layer 4. And what is the basis of this layering? So the basis of this layering is that in each layer the cone penetration resistance should be uniform or constant. Now for layer 1 it would be simply 3000 kPa, for layer 2 it would be 4000 kPa, for layer 3 it would be 7000 kPa, and for layer 4 it would be again 3000 kPa. Okay, so here I am writing, here it's QC value, so it's 3000, here it's 4000, then 7000, and then 3000. This is in Okay. Now, what are the thicknesses of this layer? So first of all, the thickness of the first layer is 1 meter, so 0 to 1. Then coming to the second layer, it's 3 minus 1, that means 2 meter. And for the third layer, it's 4 minus 3, that is 1 meter. And for the last layer, that is layer 4, it's 5 minus 4, that is 1 meter. Though the variation is given up to 6. So please keep in mind the influence zone is restricted up to up to a depth of 5. Okay, so that means the thickness of the last layer would be 5 minus 4, that is 1 meter. Okay. Now this is about the layering. Okay, so therefore this summation symbol or sign is placed before this expression. Now for this individual layer, for each of this individual layer, you have to calculate these entities H, C, sigma 0 prime and delta sigma. Now what is H? H is again the thickness of the layer, and it's very straightforward. You can easily calculate because already you have done the layering. So based on your layering, you can easily determine the thickness. What is the C? So C is the compressibility of the layer. This is the compressibility coefficient. Okay. Now you can basically take the reference of this compressibility coefficient according to two different basically researchers. So first of all, since we are using this approach, Devier and Martin's approach, so this C compressibility coefficient is given by Devier and Martin's approach is like that. So it's 1.5 QC divided by sigma 0 prime. So there is another expression valid for this compressibility coefficient as 1.9 times QC by sigma 0 prime, and that is given by Meyer. Okay, but we will not use that approach since it's mentioned in this problem that we have to restrict ourselves by the recommendations Devier and Martin's. Okay, so QC, this is the cone resistance, and this is basically given, and you can easily obtain this value for each of these layers. And now what is sigma 0 prime and delta sigma? So sigma 0 prime and delta sigma, so both these entities bear the same physical significance as we basically we have taken for the last problem. That is sigma 0 prime is the effective overburden pressure at the central line of the layer, and delta sigma is the additional stress increase at the central line of the layer. Okay, now for this problem, since we are having 4 layers, so sigma 0 prime and delta sigma, we have to calculate for each of these layers individually. Okay, now we'll start our calculation in a tabular fashion. So since we are having 4 layers, 1, 2, 3 and 4, and we can easily obtain, or we can easily write the thickness for this layer as first layer thickness is 1 meter, then the second layer thickness is 2 meter, third layer thickness is 1 meter, and the fourth layer thickness is 1 meter. Now coming from QC, so for the first layer it's 3000, second layer it's 4000, then third layer this is 4000, third layer this is 7000, and fourth layer this is again 3000. Now what is sigma 0 prime? So now for this problem, since there is no water table in the, at least in the influence zone, so it will be simply the total stress, that means the bulk unit weight multiplied by the corresponding depth. So corresponding depth in the sense, so I have basically marked the center line, means a point in at the center line level for each of this layer as A, B, C and D. So at this point you have to calculate both the effective vertical stress and the additional stress increase. Now for that you have to know its vertical coordinate from the ground surface. Okay, that is Z value. So here the datum is basically the ground surface. Now what is the Z value for A, B, C and D? So Z value, so ZA for for point A, the Z value is 2 plus 0.5 because 1 divided by 2. So this will give you the location from the foundation level, and you have to add this additional 2 to get the location from the ground surface. So 2 plus 0.5, that means 2 plus 0.5, that means 2.5. So similarly ZB, it will be 2 plus 1 plus 2 by 2. Okay, so here it's better to write 1 by 2. So 3 plus 1, 4. And ZC, 2 plus 1 plus 2 plus 1 by 2. That means 3 plus 2, 5, 5.5 meter. And finally, ZD, so 2 plus 1 plus 2 plus 1 plus 1 by 2, that means 6.5 meter. So now it becomes very easy to calculate the effective overburden. So it will be the bulk density of the sand deposit is 17 kilonewton per meter cube. So it will be 17 multiplied by 2.5. Then 17 multiplied by 4. Then 17 multiplied by 5.5. Then 17 multiplied by 6.5. Okay. Now what would be the values for sigma 0 prime then? So first of all it would be 42.5. Then second layer it would be 68 kPa. Third layer it would be 93.5 kPa. And finally for the fourth layer it would be 110.5 kPa. Please cross check these values. Okay, now coming to the compressibility coefficient, it's simply QC divided by this compressibility coefficient is given here, no? 1.5 times QC by sigma 0 prime. So therefore this C for the first layer would be 1.5 times C value, QC value for this layer is 3000 divided by sigma 0 prime, that means 42.5. So 105.9. Okay, and how we have got this value? So this value basically comes from 1.5 times 3000. This is the sample calculation divided by. Okay, so similarly you can get the compressibility coefficients for other layers as 88.2, then 112.3 and 40.6. So we have got the compressibility coefficient as well. Now the only entity that we have to obtain, that is the additional stress increase, and again for that additional stress increase you have to consider a vertical stress distribution. So as we used or considered in the previous problem, so 2 vertical is to 1 horizontal. Okay, up to the influence. This is 2 vertical, 1 horizontal as mentioned in this problem. Now how we can calculate then the additional stress increase at this point A, B, C and D? So again you have to use the same formula, that is this delta sigma, it would be Q times B plus Z1 square, since this is a square footing. Now what is Q? Q is basically the net intensity of loading which is basically applied at the foundation level multiplied by the area. Here it is B square for a square footing divided by B plus Z1 square. Okay, oh sorry, it's merging with the table. Okay, so delta sigma, it is Q b square divided by b1 plus z, b plus z1 square. Now this z and z1, now two notations are used. So z is basically, z denotes the distance from the ground surface where the datum is ground surface. However, for z1 the datum is the foundation level. Okay, so therefore first you have to calculate, because this q times b square, this value will remain constant for each of the layers, for each of the points, center line points. Only this z1 value will be varying for the calculation of delta sigma, and accordingly you will be getting a variation in the delta sigma. Okay, so now we'll calculate this z1 from the datum, okay, from the foundation level. So this z1, it would be 0.5 meter, that means half for point A, then 1 plus 2 by 2 for point B, again this is in meter, then 1 plus 2 plus half, this is for point C, and 1 plus 2 plus 1 plus half, this is for point B. So that means for point A it is 0.5 meter, point B it's 1 meter, point C it's 3.5, and point D it's 4.5. So this delta sigma, this will be 200 multiplied by 2.5 square divided by 2.5 plus z1 square. Okay, so now we will calculate the delta sigma value. So it is 200 into 2.5 square. That means the load which is basically acting, this value is basically 1250 kilometer, and this load we have to divide by the dispersed length at the concerned level. So that is basically b plus z1, and considering both the directions, length and width, it should be divided by b plus z1 square for a square footing. So therefore for the first layer it would be 1250 divided by 2.5 plus 0.5 square. So divided by 9, so it's 138.9. Okay, so this value would be 138.9. So similarly for the remaining layers it would be 61.7, 34.7 and 25. Okay, so please correct me if I am wrong in substituting these values, because I have calculated these values beforehand. Okay, so please calculate, please cross check these values. Okay, now it becomes very easy to calculate the SI value, because you have to just calculate employ this expression 2.3 times h by c log of sigma 0 prime plus delta sigma by sigma 0 prime. So if we utilize that expression given by DVR and Martens, so we can calculate the individual layer elastic settlement as 13.7 mm. So I am writing down the final value, then 14.6 mm, then 2.8 mm and 5.1 mm. Now you have to add all these values to get the final settlement. Okay, so total therefore would be 13.7 plus 14.6 plus 2.8 plus 5.1, 36.2 mm. So this is the settlement calculation part depending on the cone resistance values and according to the approach recommended by DVR and Martens. Now unlike the previous problem, here no statement like do not apply this correction, any correction is not mentioned here. So therefore we have to incorporate the applicable corrections to get the final answer. Now how we can get the final value? So the final value to get the final value, we need to incorporate two correction for elastic supplement. As you know that first of all you need to incorporate the depth correction and then rigidity correction, because pore water pressure correction is not valid for elastic supplement or the immediate supplement. Now if we consider the supplement as flexible, so since rigidity is mainly arises due to means in case of wrapped or matte formulation, so this is not valid. Okay, now the one and only correction which remains to apply is the depth correction. Now how to incorporate this depth correction? So to incorporate the depth correction factor, we'll refer this chart, this figure given in IS code. So where to get the depth correction factor, so in x-axis this is the depth correction factor is given with the normalized depth. Now here the depth of the foundation is normalized with respect to square root of the dimensions, both the dimensions, the length and breadth, and these plots are given for various L by B ratios starting from 1 to 100. So this is 1 and this is 100. So therefore to obtain the depth correction factor from this figure, we have to calculate first two normalized values. Okay, so first of all this dF upon L times B and L by B ratio. Two ratios we need to know. So for the given problem, the dF value is what is the dF value? The dF value is 2, and the length and breadth or width, both the dimensions are equal for a square footing, and it's 2.5. So that means 2 divided by 2.5. 2 divided by 2.5, 0.8. And what's about the L by B ratio? It's 2.5 by 5. Now considering these two ratios, you have to calculate the depth correction factor from this figure. So the depth correction factor, it would be, so where this dF under square root this LV 0.8, so this is the 0.8 value. Okay, and this is cutting this graph plot here. So this is the right hand curve is basically giving the correction factor for L by B 1, and then it's as it shifts towards the left side, so the L by B ratio is increasing from 1 to 100. So 1, then 9, then 25, then 100. So you have to consider the extreme right hand side curve for calculating the depth factor for this problem. So it will be almost in between 0.65 0.75 to 0.8. okay, so 0.75 to 0.8. so this depth correction factor we can take it as 0.77. this is from the figure 12. Okay, so here something here will be getting the value. So it's 0.7, it's 0.8, so this is 0.75. so in between 0.75 to 0.8, so you can approximate this value as 0.77. so therefore the corrected value, so the corrected immediate settlement would be 0.77 times 36.27.9 and this is the yeah 36.2 multiplied by 0.77, that means 27.9, so almost 28 mm. Now this is for considering only the depth correction factor, and you are assuming the footing, given footing, as a flexible footing. Now if the footing is not flexible, suppose for a footing which is mat foundation or wrap foundation, then you have to additionally incorporate the rigidity correction as well, and for that this rigidity correction factor you can take it as 0.8 as recommended by previous researchers. So you have to additionally multiply 0.8 with this value to get the final corrected answer. Okay, so this ends our problem 4. So I hope it's almost 6:55, so we will not be able to solve the remaining problems in its full length. However, we'll start to explain a little bit about the problems, and we'll take these problems as homework, and if we face any difficulties in solving these problems, we'll start our next session with these problems. Okay, so this problem 5 is regarding the results of two plate load tests for a supplement of 25 mm are given like this: plate diameter and the load. So 31 kilonewton load is basically obtained for a supplement of 25.4 mm using a plate diameter of 0.305 meter, and for a plate diameter of 0.61 meter for the same settlement the load is obtained as 65 kilonewton. Now a square column foundation is to be designed to carry a load of 800 kilonewton with an allowable settlement of 25.4 mm. So again, the column foundation which you have to design for a load of 800 kilonewton. So for that also the allowable settlement will be 25.4 mm. That is same settlement as experienced by these plates, okay, during the plate load test, or the load which is basically given corresponding to the same settlement. Now determine the size using Housel's method. So through this problem we'll understand how to utilize the data of a plate load test to determine a required size of a square or any say column foundation for which the settlement value is not changing. Okay, so the data, the plate load test data or the load which is basically given corresponding to 25 mm settlement, and the square column which is to be designed, the allowable settlement for that the square column should be the same, 25.4. Now how we can solve this problem? So to solve this problem, so first you have to know about this method, Housel's method. So Housel's basically provided one equation considering this perimeter, cross-sectional area, load and two coefficients. Okay, so he has given the load of a plate P, or not P, Q, that can be sustained by a plate of diameter, any diameter or any cross section. It may be square, it may be circular. Okay, so it would be M P plus N A. Now here this M and N, these are two constants, arbitrary constants. Okay, and this P, this is the perimeter of the plate, since the plate is circular, so it would be pi d for this problem, and A, this is the cross sectional area of the plate. Okay, cross sectional area plate, okay, pi square, and this is the load. Okay, so what you have to do first? So first you have to utilize the given information and you have to calculate this coefficients m and n. Now how? So for plate 1, this equation would be mp1 plus na1 equals to q1, and for plate 2 it would be mp2 plus na2 equals to. Okay, I will not solve this problem, so I am just explaining about the approach you should follow to get the required result. Now you know P1 and A1 and Q1 for plate 1, because P1 it's simply pi d, you know 0.305 meter for plate 1. So therefore the perimeter would be pi times d and the cross section area would be pi d square by 4, and Q1 is 31 kilonewton. Similarly for plate 2 you can calculate P2 and A2 value, and it's given to you the Q2 value as 65 kilonewton. Okay, so if you substitute these values for P1, A1, Q1, P2, A2, Q2, so you will be ending up with two equations, means a system of linear equations where the only unknowns would be m and n, and you can get the values of these unknowns by solving this equation. Okay, so if you substitute the values for P1, A1, Q1, P2, A2, Q2 in equations 1 and 2, then you will be ending up with a system of two linear equations, and if you solve this system of linear equations, you will be getting the values for this unknown coefficients m and n. Now for your easy reference, I am giving you the values which I have calculated. So m will get as 20.5 and n value as 30.8. So it's after solving. Okay, after solving these equations you will get the values for m and n as 20.5 and 30.8 respectively. Now what you have to do, you have to basically design a square column foundation which will carry a load of 800 kilonewton and with an allowable supplement of 25 N. Now since you know the load which is against which the column or the column foundation should be designed, so what would be the area then? So area, it would be simply, so first of all the load you can calculate. Suppose, so since this is a square foundation, this is a square column foundation, so the size of the footing we are taking it as D. Okay, so now what would be the load then? It can sustain with the same allowable supplement, so it would be m 4 times b. So this is nothing but the perimeter of the square column footing, and n times b square. This is the, okay, sorry, I have done a major mistake here, because this p and n, these are basically interchanged. Okay, so this is a, this would be p, then only this m and values you will be getting anyhow, otherwise you will be getting these values in the reverse way. Okay, so this would be So therefore these values would be b square, and this value would be b. Okay. So this load against which the column foundation should be designed, this is given as 800 kilonewton. Yeah, 800 kilonewton. So therefore, the equation you can modify in this fashion, that 20.5 times b square plus 4 times 30.8. So 4 times 30.8, it would be 23.2 b minus 800 equals to. So you will be having this equation, a quadratic equation for the variable b, and which you need to calculate. So therefore, if you solve this equation, you can easily determine the value for b. So the value for b I am also giving to you. So it would be approximately 3.393 meter. So rounding up to. Okay, so this would be the answer. So please solve this problem in its full length, and in between, if you face any difficulties, please let me know in the upcoming section. So this is for problem 5, that is utilizing the data of plate load test, design of a square column foundation against a specific load, that is 800 kilonewton, using House's method. Okay. So please keep in mind that here the allowable supplement for the design column foundation and the supplement against which the plate load test data are given should be same. Okay. Now this is the last problem for today's session. So this problem is taken from GATE examination 2017. So this problem is stated like that: the plate load test was conducted on a clay strata by using a plate of 0.3 meter by 0.3 meter dimensions. The ultimate load per unit area of the plate was found to be 180 kPa. The ultimate bearing capacity of a 2 meter wide square footing would be. So this is a very simple problem. So if you know the fundamentals, then you can easily answer to this problem. So here the ultimate bearing capacity or the ultimate load per unit area of the tested plate, square plate, is given as 180 kPa. Now you have to extrapolate the ultimate bearing capacity for a 2 meter wide square footing using this information. Now what would be your answer? And the soil deposit is purely cohesive in nature, that is a clay strata. Okay, so in the previous session we discussed about a few factors which can affect the ultimate bearing capacity. So as I can remember, the nature of soil or width of the footing, depth of the footing were a few factors which can affect the ultimate bearing capacity. Now we'll see. So in that means, in addition to that, I also discussed that in some specific circumstances, this width of the footing or depth of the footing will not be having any impact on the ultimate bearing capacity, and this is a typical example for that statement. Okay, how? So if we consider the Tirjaghi's bearing capacity theory, so this QU we can write it as alpha 1 CNC plus gamma DF NQ plus alpha 2 gamma B N gamma, and we know alpha 1, this is 1.3 for a square footing, and alpha 2 0.4. Now since this is a cohesive soil, first of all this N gamma will be 0. So since phi equals to 0, so NC would be 5.7, NQ would be 1, and N gamma would be 0. Again, these bearing capacity factors are in accordance with Terjagi's theory. Okay, given by Terjagi. So therefore, as you can see, there is no effect of the footing dimension on the ultimate bearing capacity. Okay, so therefore there is no effect. Now, what is about the second component? Now, for the second component, as you know, for conducting plate load test, you have to excavate a pit of dimension 5 times BP. If this dimension is BP, plate dimension, so 5 times of BP you have to excavate. That means there is no surcharge. There is no surcharge. So again, this component, this whole component, the surcharge contribution will be 0. So that means this QU will be simply alpha 1. So as long as you are dealing with the same soil deposit, so QU will be independent of the depth of the footing as well as width of the footing. So therefore, for this problem, since you are dealing with a clay strata, so there will be no such impact on the bearing capacity. If you change the size from a plate size of 0.3 by 0.3 meter square to a footing size, square footing size of 4 meter square. Therefore, the ultimate bearing capacity will remain same. So it would be 180 kPa only. And why? Just we have explained. Okay. So this is the. Okay. So now we'll end this session by taking one homework problem. And this problem is again related to plate load test. So a plate load test was performed on a granular soil deposit using a 60 centimeter square plate at the same depth of a 3 meter by 3 meter foundation that is to be constructed later. A 5 mm plate supplement was found from the load supplement curve for an expected foundation load of 1200 kN. What would be the estimated foundation supplement if the water table was 2 meters below the base of the foundation? Use Terjagi and Pett's method to estimate the supplement and IS 8009 method for water table correction. So in the previous problem, we have seen how to extrapolate the information of bearing capacity of a tested plate to bearing capacity of a given foundation. So utilizing the information regarding bearing capacity of the plate, how we can determine the bearing capacity of a given foundation. Now, through this problem, we'll understand how to calculate the settlement or how to extrapolate the settlement of a tested plate to the settlement of a given foundation. So, where the settlement of the plate is given as 5 mm. Okay, for an expected foundation load of 1200 kN. So, this is the information given for plate which is tested in the field. Now what you have to determine? You have to determine the estimated foundation settlement of size 3 meter by 3 meter and where this depth of the foundation and depth of the plate remains same. So this is the principle of the plate load test. So the plate should be tested at the same depth where the footing will be constructed in the near future. So depth will not vary in general, though in some cases it can vary. Then you have to accordingly implement or incorporate the depth correction factor. However, there is no need of such correction factor since it's mentioned that the plate is basically tested at the same depth of the foundation. Okay, only the discrepancy in between two scenarios lies in the foundation, in the water table location. So, as you know, when you will perform the plate load test, if you encounter some water table in between the depth of the plate, then you have to basically pump out the water before performing the test. So, therefore, the settlement what will be obtaining from performing the test, so there will be no such effect of the water table. However, in the real case, it's observed that the water table is located 2 meters below the base of the foundation. So therefore, here the question arises that how the settlement obtained for this plate is corrected for the water table to obtain the settlement for the foundation, given foundation of size 3 meter by 3 meter. And again, this is a granular soil. So how we can address this problem? So we can address this problem by the method given by Terjaghi and Pegg. So Terjaghi and Pegg given the correlation between the plate settlement and the footing settlement in this fashion. So SA, if this is the settlement of the footing, and SP, if this is the settlement of the plate, then this would be VA times VP plus 30 divided by VP plus 30. Again, please keep in mind that this expression is only valid for granular soil. Okay, and this VA BP, you should incorporate these values in NPTEL. So then only you can get the correct answer. Now here you know the plate settlement, you know the dimensions of the plate, that means width of the plate and width of the footing. So you can easily determine the settlement of the footing, expected or estimated settlement of the foundation of 3 meter by 3 meter. However, you have to correct this settlement for the water table, because at the time of testing there was no water table. However, in the time of construction you have encountered the water table at a depth of 2 meters below the base of the foundation. So the corrected settlement would be SA divided by this correction factor CW. Okay. Now how you can calculate this CW? So CW, as per IS 8009, it would be 0.5 plus 0.5 BW prime by B, but it should be less than 1. Okay. Now B, you know the width of the foundation as 3 meter, and what is DW prime? DW prime is basically measured from the foundation level. So this is your water table. DW prime, and for this case it is 2 meter. Okay, so therefore you can easily calculate the CW. Now once you know the CW, you have to just divide the uncorrected settlement by the correction factor corresponding to water table. So you can easily get the corrected final settlement or estimated settlement of the given foundation of size 3 meter by 3 meter. Okay, so I'll request please solve these problems in its full length and let me know about any difficulties which we'll face in the upcoming session. Okay, so thanks a lot for joining this session, and for your kind information, we'll again meet on next Sunday, that is on 27th August at 5 p.m. Okay, so if you don't have any problems, then I can end this session here. Otherwise, I will wait for a few minutes if you have any doubts or if you need further clarification.